Okay, so here we're going to go over finding domain and range. All right, so in our previous section, we went over what the domain was, what the range was for a relation. Right, and here we're going to be looking in context of our functions. Right, so we're just going to go over a few examples here. Right, so let's just start off by finding domain. Right, so in this example, so you want to find the domain. Let's say we're given a set of ordered pairs, right? 5, -4, 10, -8, and 15, -12. All right. Okay, so we have our relation here, which looks like it is a function, right? But here we're just asked to find the domain. Remember, domain represents the first part of our ordered pair, right? So we'll say here, using our set notation, the domain is the first coordinate in our ordered pair. So here we'll have -5, 0, 5, 10, 15. All right. Okay. All right, and that is the domain of something like this. Right. Now let's say that we had something that is right. We can't just pick it out. Right. We don't have a finite set of ordered pairs. Let's say instead we had an example where we were asked to find the domain. Domain f of x 5 minus x plus x cubed. Okay. All right. Now, whenever we have a function, well, here, remember, a function, it essentially represents an infinite number of input values, possibly, right? Now, if we want to find the domain, the one question that I want to ask myself, are there any restricted values? Are there any values that I plug in for x that are going to give me something that is undefined? Right. Now, something that would be undefined would be if I'm dividing by 0, right? That is an undefined value. If I'm taking the square root of a negative value, right? That is also undefined. Right? So I think those are the two major operations that'll show up in this course where you say, oh, that is going to be undefined. Now, looking at something like this is what's called a polynomial, which we'll cover extensively in a future section. But looking at something like this, I don't have any of those restrictions. Right? There are no, x can be any value, right? If I put in 1, if I put in 0, if I put in -1, if I put in 5,000, right? I can find the number, right? It'll be a large number, but I can still find it. So there are no restrictions, right? So for something like that, we say, all right, the domain is all real numbers, right? Now, how can I represent that? Now we're going to look at 3 mathematical ways to represent it, right? So just kind of using our words, we could say, oh, that's all real numbers, right? Let's say here. Domain is all real numbers. Using kind of a fancy math notation, use this fancy looking R here to represent all real numbers. All right, now it's kind of just using our words. Now, if we want to write this using some mathematical symbols, well, we can do this a variety of ways, right? Our input value is x, so we can use it using some kind of interval here where we use our parentheses here. Now, when dealing with infinity, they're always going to be open, right? So it's open from negative infinity to positive infinity. Okay? So this would be using interval notation. All right. Now, We can also use some form of a three-part inequality here, where we could say, all right, in this case, since x falls, well, any real number, we can represent that using an equality by using these values right here. Right, x falls between infinity and negative infinity, essentially all real numbers. Right, inequalities are always strictly less than, strictly greater than. These are using equalities, or excuse me, inequalities. And the last way that we can do this is using what's called a set builder notation, where again, if we're representing a set, we use these curly braces, right? So we say x such that, now in this case, we can do one of two things. We can use our inequality, right? Or we can also do x. This little bar just says such that, right? And representing x such that x falls, whatever this rule is. In this case, all real numbers. Or I can also use this type of notation. X is the element of some real number. All right, and this is what is known as our set builder notation. Okay. All right. Okay. So now let's take a look at another example here. Let's say I want to find the domain of f of x equals to 1 plus 4x over 2x minus 1. Okay. Now, in this case, right, again, we want to ask ourselves, what are some values that would make something like this undefined? Right? Because I want to exclude those from my domain. Right? When we're asking ourselves find a domain, we're looking for values that when I input into my function, I can get a result back. In this case, a real number resulting back. Now, as I mentioned in the previous example, we have to watch out whenever we're taking a square root of a negative. We don't want to do that. Those would be undefined values. Well, not necessarily undefined. They're complex numbers, but here we're strictly dealing with real valued functions. Okay, so we're looking for a real valued output. All right, so we're not taking a square root here, so I don't have to worry about that. What I do have to worry about, the second condition, is am I possibly dividing by 0? Well, here we have a fraction, so that is a possibility, right? So I want to make sure that I never divide by 0, because that is going to give me an undefined term, right? That is going to give me something that is undefined, and it would not be part of my domain. All right, so when would this be 0? This would be 0 whenever the denominator is 0. The numerator can be 0, that's fine, right? 0 over any non-zero number is just 0. Okay, so that is fine. I cannot have 0 down here, right? So 2x minus 1 cannot be 0. All right, and you can treat this like an equality, like let's just solve for x to see what value that is, right? 2x cannot equal 1, divide by 2. X cannot equal to 1/2. Okay, so that is my only exception. X can be any other value, right? Any other value, even if it's a negative 1/4, which would give me 0 in the numerator, which is fine. All right? But anything else, right, is okay, right? Except 1/2. 1/2, when I plug it in, I get a 0 in the denominator, and that is just undefined. But everything else, perfectly okay. All right, so how do I represent that? Okay, so here we can solve this. Again, we can set, if we use our interval notation, All right, we can go from negative infinity, right, which would be, again, almost like you're reading from left to right, the smallest value, right, smallest in the negative direction, negative infinity. Now, all of these are valid except when they get to 1/2. So to signify that, I'm going to use a union notation. All right. Okay. So that would be our interval notation, right? Now, when we have the parentheses instead of the square brackets, that means that 1/2 is not included. And I don't want to include it here, right? So this will include from the left all the values from negative infinity. Again, if I look at a number line, all the values here on the left from negative infinity. And then on the right, all the values not including 1/2, but bigger than 1/2. All right, so it includes every single value except the 1/2. All right, now using our set builder notation, the domain would be x such that x is less than 1/2 or x is greater than 1/2. All right, so that represents the same thing I have up here. Okay. All right. Okay. So now here, let's take a look at finding the domain and the range. Right. Now, I'm going to take a look here. In our previous section, we talked about we were given these toolkit functions. So here, so what we're going to do here is we're going to take a look at our toolkit functions and we're going to find the domain and range from the graph. All right. Okay, so here for our constant function, all right, notice here when we're looking at domain, are there any values that are not allowed? Right? It doesn't look like it. Right now, it's not written here, but we got to make sure that we say that this is going in both directions. All right, so looking at the domain, there doesn't appear to be any restrictions. So the domain is from negative infinity to infinity. Right? Now our range, now looking at this, these are the y values. Now this particular function is f of x equals 2. Right? So f of x is a constant function. It doesn't take any other value other than 2. All right, as we can see, we have a horizontal line. So the range here is simply the number 2. Right? One element, it is always from negative infinity to infinity 2. All right, let's take a look at our next one here, the identity. All right, now if we look at our identity function, if we look at the domain, right, again, there's no restrictions from negative infinity to infinity, and there's also no restrictions from the range either, right? It goes, again, down this way in the negative direction and up here towards the positive direction. So in this case, our range is also the same as our domain, from negative infinity to positive infinity. All right. And now moving on here to the absolute value. All right, so looking at, again, the domain, the values along the x, does not appear that there are any restrictions here, and there isn't. So the domain is from negative infinity to infinity. All right, now what about the range? Now again, range, we're looking along the y values that it attains. Notice here that there are no values below 0. All right, so in this case, the range is inclusive of 0 up to infinity, right? Infinity up in this direction. All right. And then moving on here, we have f of x is equal to x squared, or quadratic. Right? And again, this is very similar in terms of the values, the domain and range of the absolute. Right? Looks like it attains all values along the x. So the domain is from negative infinity to infinity. Right? And the range are all non-negative numbers, right? Starting at 0 and going up to infinity. Okay. Alrighty then. Now, moving on here, looking at this one here, the cubic, excuse me. Alright, again, no restrictions along the x or even the y, right? This kind of grows up in the positive direction and decreases down in the negative direction. So I think here, similar to our identity, we have the domain is all reals, and the range is also all reals. Okay. Now here, for our square root, here we have, notice here there are no values in our domain that are negative. So our domain, inclusive of 0 to infinity, excuse me. Oh, pardon me. All right. Now our range, again, looks like it starts from 0 and then it increases the further and further along we go. So the range is similar. All right. Okay. And then moving on here, our cube root. Again, notice here no restrictions here along the x or the y. So the domain is negative infinity to infinity, and our range is also from negative infinity to infinity. All right, and our reciprocal function, right? Notice here there's a break here where it's undefined. Right? We can't divide by 0. All right, so our domain is going to be all real numbers here except 0. So again, the way we do that is from negative infinity, 0, union with 0 to infinity. All right, where we kind of just take out the 0 there. And the range, similar, right? It looks like it decreases down here, and then it looks like it's almost approaching quite 0, but we're never going to get to 0, right? The reason for that is 1, right, divided by any number, right? Whatever that number is, you're never going to get a 0. Right? You're going to get a really small number the further out you go here, but it never actually is going to attain the value of 0. Okay, so the range is going to be the same here. 0, union. All right. And then lastly here, our reciprocal squared. All right. Here we have kind of a break since we can't divide by 0. So the domain, similar, negative infinity, 0, union with 0 to infinity. And then the range, notice it's only positive values since we're squaring here, but it's not going to be 0. Right? So from 0 to infinity. All right. And that is the domain and the range of our toolkit functions. Okay, now let's say we were asked to find the domain and range here of a function. Let's say, all right, let's do one last example here. Let's say I want to find the domain and range okay. so we have a square root here. So now we do have to, in this case here, the domain, right? I have to make sure that everything inside the square root is either 0 or positive, right? So whatever this quantity is must always be non-negative, essentially, right? So what that means here is, so let's start by the domain first, right? Okay, so for the domain, right, this value must be 0 or greater than 0. All right, so let's find out what values of x that works for. So subtract 2, and we get negative x greater than or equal to negative 2. All right, but I'm not looking for negative x. I'm looking for x. So what I'll do next is I'll multiply both sides by negative 1. All right, now here we do have to be careful when dealing with inequalities. Multiplication by a negative is going to turn my inequality around. So this becomes positive x, but now instead of greater than, it's less than or equal to 2. All right, and then notice that this checks out, right? This, if I plug in 2, I get 0. But if I go above 2, let's say 3, 2 minus 3 is negative 1, and that's not going to work. That's undefined. But if I go in the other direction, right, less than 2, let's say 1, 2 minus 1, that's 1, that works. 0, if x is 0, right, 2 minus, or even 2, right? 2 minus 2 is 0, that checks out. 2 minus 1, 2 minus 0. 2 minus, let's say, a negative 3, that makes it positive. 2 plus 3, 5. So that works out as well, right? And this in interval notation is this interval right there. So that's our domain. All right. Now what about the range? Now for this one, I'm going to use my knowledge of just kind of the square root, right? The square root, in fact, is one of my toolkit functions. Right? Now this minus, 2 minus, whatever's going on here, this kind of just changes the values along the x. In other words, the domain. All right. But it doesn't change the range. It still maintains the general shape. The only thing here that is going to change the actual range is, what does it do here, right? What does this negative do, right? All the outputs from the root are positive, but the negative is going to make them all negative. So in fact, what's going to happen here, right? Our range is going to be from negative infinity up to and including 0. Right? Because what happens is this flips everything across the x-axis. All right, so my range is going to be from negative infinity to 0, inclusive of 0, right? We saw when we plug in 2, the output is in fact going to be 0. All right, and that is going to be my range, right? And I take that from my from my knowledge of my toolkit functions. All right, in a later section, we'll get all through translations and transformations of graphs that we'll see. We'll go more into depth of how those work. All right, thank you.